Okay, welcome. Welcome everyone to another quantum hardware lecture. Today I'm planning to talk about the box 7.6. That's about the energy levels of an atom in the Nielsen Schwann book. And what he did in this box is just make a very brief summary about the how you solve the Schrödinger equation when we're dealing with even the simplest atom, that's the hydrogen atom. And I'll make a summary as well, but with a little bit more detail than we have in this box. So the idea today is to do this, and then in the next lecture we start like making mixing the subject from the last lecture that we saw how photons behave like in a cavity with two mirrors. That's the Fabry-Pérot cavity. And the idea when we do computation, we put like some atoms inside this cavity. But in the theoretical point of view, it's important we know at least how to solve the Schrödinger equation, because you need like the wave function associated when we're dealing with this interaction of the photons and the atom in the cavity. So, but again, if we see like a complete the complete development in the theory, how to solve it, we will need like at least 2 or 3 lectures. So my idea is to give a summary and tell you the references. It's basically the coin, but you can find another quantum mechanics books, the things that I will talk about. And yeah, unfortunately, we can see not with all details, but I'll give a better, a more complete summary than in the Nielsen Schwann book. So okay, let me just give a brief introduction in these slides, and then we go to the whiteboard. So okay, today we will talk about the box 7.6 and the energy level 2 level atoms. So we have discussed in previous lectures the behavior of the photons and the interaction of these photons with nonlinear, semi-classical nonlinear medium. That's the optical model, the first optical model that we study. And we saw like there is some problems. First of all, because the nonlinear medium, usually the effect is very small. And the other problem is that this medium it has a lot of atoms and molecules inside the medium, of course, and this could like increase the decoherence of the computational when we try to do computation. So another option that we start in the next lecture is you try to increase the nonlinearity, not in the medium, but using not a non-linear medium, but using what we call the Fabry-Pérot cavity. And the idea we can increase the intensity of the electrical field that you put inside this cavity that has 2 mirrors, and then you can have a biggest power inside the cavity once the photons is bouncing back and forth inside the cavity. And yeah, but we'll do the computation making these photons interacting with atoms that in the future we put inside this cavity. But to do this, let's first understand a little bit about how you can like deal with the solutions, for instance, for the Schrödinger equation when we are dealing with atoms. Okay, so this is the idea of this box 7.6. And again, we see some brief summary, more complete than in the Nielsen Schwang book, and I'll cite like references if you guys want to see more complete review. So the electronic energizing states of an atom are described in box 7.6. And in this context of quantum computation, modeling an atom as having only two states is an excellent approximation. So we are considering when we are modeling, like to do quantum computation, we are considering what we call a two-level atoms. Okay? So this two-level atom approximation can be valid because we show the concern with the interaction with the monochromatic light that we studied in the previous lecture. So in this case, the only relevant energy levels are those satisfying two conditions: that the energy difference between the atoms match the energy of the incident photons, in the case of the monochromatic field, and the symmetries do not inhibit the transition, these symmetries. We'll see a little bit, we'll comment a little bit more on this in the future. So these conditions arise from basic conservation law of energy, angular momentum, and parity. So since the energy, as you saw in the past, of like a oscillator, no? A simple harmonic oscillator is given by this expression, h bar omega, n is the number of levels of energy that we are dealing. So energy conservation is no more than the condition that the total energy is this difference. So E2 is the second eigenstate, or the second level in the atom. E1 is in the first level. So if you take this here, E2 minus E1, you have this, where E2 and E1 are two eigenenergy of the atoms. Okay? Okay, angular momentum and parity conservation requirements can be illustrated by considering the matrix elements of R, this R operator, with the position between two orbitals, wave functions. That's the wave functions for orbitals usually are represented in this way in terms of the quantum numbers that we will comment soon. Okay, so L and M are quantum numbers from different orbitals here. So without laws of generality, we can take R to be in the XY plane, such that it can be expressed in terms of the harmonic, spherical harmonics. So today, let's see the box 7.6, where we study a little bit and understand from where this type of functions that called spherical harmonics is coming. Okay. So on the whiteboard, we studied some quantum mechanical properties of the atoms. Since this is a very well-studied topic, which is present in several quantum mechanical textbooks, our intention in today's lecture is to give a basic review of this subject. For those interested, we will suggest references during the presentation where more detailed study can be done. Okay? Unfortunately, we cannot see the whole details because we will need at least like 2 or 3 lectures, extra lectures to see. But let's comment, and then if you guys have doubts, like maybe we can do like extra lectures, doing this a more complete study about what the things that we will comment today. So again, we are here in the whiteboard. Let's box 7.6 energy levels of the net. So okay, so in general, the electrons of an atom behave like particles, behave like particles in three-dimensional box. It's the way that we do in general to like solve the Schrödinger equation with Hamiltonian of the form. So in general, the Hamiltonian, change the column, age of the atom is given by the energy, kinetic energy of the atom, P square is momentum over 2m, minus Z is the atomic number that depends on the number of the protons that we have, RK. Plus a complete description we would have, but in general, these extra terms here, at least for atoms with the atoms with few electrons and protons, usually these terms are very small, but we will comment them today. So we have this term that is a type of relativistic term. This other term that is a Hamiltonian that's related to the interaction between the electrons. This is a Coulombian potential. We have a Hamiltonian related to the interaction of the spin orbit that will comment, and a Hamiltonian related with the hyperfine structure that will comment soon. So this is equation 761, 61 in the Newton-Schwenk way. So okay, so each term, let's do in the Newton-Schwenk way. This term here describes the electrons kinetic energy where pk is the momentum of electron k, and m the electron mass. Electron mass. Okay. So this term will be always present. That is the usual. We are always dealing with it. The other is this one. This term is the Colombian attraction between the electron that is negative, that has a negative charge, Colombian attraction in between the electron its negative charge to the between the electron and the nucleus. And the nucleus, that's positive. And RK here, RK is the position of electron K. Position relative to the nucleus, right? You have the nucleus here and the electron here. So in this case, AK is this. And Z is the atomic number. Z in the atomic number. Okay, so in general, these terms are the two more important, more relevant. But let's do in the and when I'll give the at least the steps how to solve the Schrödinger equation. I will consider only these two terms. But let's first analyze the other possible terms. So this one, H L, is a relativistic correction. So this is a relativistic correction term. And the real explanation from this term comes from the Dirac equation. But we can make a like approximation and put this Hamiltonian here in terms of the relativistic energy. So just to remember in special relativity, the energy of the system is given by E squared, the energy, relativistic energy, c momentum, speed of light in the vacuum, pc squared plus m squared c to the 4. And you can write this as square root of this p squared c squared plus m squared c to the 4th. And you can write this as c p squared. But you can p squared plus m squared c squared. This minus c to the 4th. And then it's square root of this. Okay. And you can make an approximation, and you can write E as mc square. We put c outside. P square is m square c square plus 1. And remember, momentum is P and V, but in general, V is much smaller than C. So you can have an approximation here. It's mc square, and you can expand this term. That will give us this P square, m square c square, minus p to the 4th, a m to the 4th, c to the 4th, plus other terms. So, okay, so the energy here is mc square. That's the famous equation, relativity, spatial relativity, the rest mass equation. Rest mass of the electron here, plus a kinetic term that is p square, and this m goes away with this m, and c square with c square. So 2m kinetic energy and plus this, that's the relativistic correction. P to the 4th, 8 m to the cube c square. Relativistic correction. Plus the other terms. So the Hamiltonian associated with this relativistic is this terms. It's my correction. So H relativistic is about plus p to the 4th, 8 m to the cube c squared. Okay. But this in general is very small. You can see the order of magnitude. H relativistic with the H kinetic, the relation of these two terms, for instance, you see that p to the 4th, 8 and c squared over p squared to m. This will give something that's about this v squared over c squared. That is something about to for the usual v. This is something about 137 square. That's about alpha square, where alpha is the structure, fine structure constant. This is for the hydrogen atom, okay? These values. Hydrogen atom. So this is about 10 to the minus to the 4th, the correction. Questions?
Mohammed Reza is asking why that relativistic correction is negative.
Oh, it's just the expansion. If you expand that term, it will be negative in the expansion, no? I think it is. You just had to expand this, that me show there. I think if you expand this term here, this next term is the negative. It will be this negative, the expanding this. Or maybe I took wrong, but I think it's negative. This term here, when you expand this.
He's asking for an intuition.
Intuition about I'm not sure if I understand intuition about what about it. The intuition in general, this is very small, and this is the idea that I think that the idea in the Nielsen Schoen book was just to show like the general form for the Hamiltonian of an atom, but tell that in most of the cases we can use like only the two first terms. That's okay, because these other extra terms that we put here in terms of Hamiltonian that we will define usually are very small compared with the two main terms. Okay, so I'm not sure that exactly this we're asking, but if not, you can send a message. So okay, if no problem, let's keep going. But if we still have questions, you can like interrupt me. It's no problem. It's just because we still have many things to do. So this other term, so this is very small, in general, because of this, even to the hydrogen atoms. So to other higher level atoms, this term will be relevant. And in general, we need, sometimes it will be necessary using even like the Dirac equation, because the Dirac equation is relativistic since his formulation. Schrödinger equation is not a relativistic equation, so we'll put in like these extra terms to make corrections. But for atoms like the hydrogen type atoms, so this correction is irrelevant. Okay. So these other terms, this the interaction of when you have two electrons. So these terms describes electron couplings. The example, for instance, of this is for helium atoms, where this EE is about E squared and R1 minus R2, where R1 and R2 are the position of the two electrons. So you have something like the nucleus. Let's say an electron here, an electron here. So this is R1 minus R2. Okay. But if you are dealing like hydrogen atoms, for instance, this will have only one electron, so we don't need to worry about this stuff. So another correction is this one. That's the Hamiltonian that's related with the spin-orbit interaction. So the spin start coming. Again, a more complete solution for this would be like a Dirac equation, because the spin is inside this equation, in the construction of the equation. In terms of Schrödinger equation, the spin comes as an extra postulate, and we can like correct with an extra Hamiltonian. But we see, we'll see that in general this correction will also be small. So this is the spin orbit. Spin orbit interaction. Which can be interpreted as the spin of the electron interacting with a magnetic field generated by its orbit around the atom. Around the atom. So if we have like the electron in the orbit around the atom, it will generate this charge in moving, will generate like a magnetic field. And we know that the spin, like in, for example, from the Stern-Gerlach experiment, we know that the spin of the particle, the electron, interacts with the magnetic field. So this will be like a type of self-interaction of the spin with the magnetic field that was produced by its movement. The spin of the electron with the magnetic field. That's not an external magnetic field, but it's the intrinsic magnetic field from the movement of the electron. So in general, this term is something proportional to this. In square c square 1 r to the cube, the product between the angular momentum and this angular spin moment. So I don't know about my time, but if my clock's not here, let's see what's time. Because we could like develop a little bit more this term is. But let's try to understand at least how you can get for this term. Okay. So the physical origin of this term. I just put here, but physical origin of HSU. So we know that the electron has velocity given by this momentum and mass. And the electrostatic field created, let's say, by the proton. So this is the velocity of the electron in the electrostatic field E created by the proton. Okay, and special relativity says that in general, it should appear in the electron reference frame a magnetic field. That we know is related with the velocity and and the electric field in this way. Okay. So since the electron possesses an intrinsic magnetic moment, it's given by this Q as vector M. Okay, that's the magnetic moment related with the spin. It interacts with B given the corresponding interaction energy. So this energy, the energy of the interaction that we are calling the Hamiltonian, okay? The spin object, which is given by this scalar B. The relation of this guy. So this is the spin interacting with the magnetic field. So okay, so this expression is minus Q S over M scalar B, where B is minus 1 C square wave vector P. But the electrostatic field, E is equal to this Q the potential for the electron dr, and V is this minus Z square over R. So if I use this E here, this V, VE, this VE here, I will have the Coulombian potential, right? So it's better to do this way, be more direct. So H is minus Q S M scalar minus E C square V back this guy here. Minus 1 over Q D V dr. And this is a vector, so I forgot what here. Huh? This is a vector R over R. So R over R. Okay. So this is Q S M is scalar 1 over C square dV dr V whole R over R. And just to go have the expression that I showed in the beginning, V is P over M. So P over M. So H, you have, I forgot this Q here. It's missing. I have a Q here in the denominator. So H will have 1 and R, and this M, this R, and dV, dr, V, yeah. If I use this here, so I will have P over M times R. But I forgot this S here, right? So I have a S is scalar this guy. And I missed this C squared too. So there's a C squared. Okay, the C square is here. This R here. This R here is this denominator. This M here is this M. C square here. This C square. Q goes away. And this extra M and P is the V. Okay. So in the end, we'll find That's this one. M squared, C squared, R, dV, dr, S scalar, P co R is the definition of the angular momentum. Okay. And V is just minus E squared over R dV dr is E squared R squared. So this term is E squared M squared C squared R to the Q L is scalar S. Okay. That's what to say in the beginning. So this is origin, like the electron has a spin associated with, has a momentum associated to the spin, and this makes the electron interact with the magnetic field. And this like magnetic field that was generated by the movement of the electron around the proton. So this we can like see magnitude as to compare with the other Coulombian term. Let's see the Coulomb. So this is about this term here that we just found. E squared S by M squared C squared R to the Q. And the Coulombian term, that is this term. But in general, L, I don't have time to show this. In general, it's about H bar. In fact, yeah. In fact, H bar is square because both are the order of H bar. Okay. So this term is about E square, H bar square, M square, C square, R to the Q, E square, R. And this is about H bar square, M square, C square, R square. And for R, the order of H bar square, electron mass times E square, that is the Bohr radius. Bohr radius for the hydrogen atom. So we would find that this term is about, again, e to the fourth H by square C square. That's about alpha, the structural constant, fine structural constant. It's about 137, or 10 to the minus 4. Okay, so the other term that he puts, but I think we will not have time to develop so much. So hyperfine interaction, you just define. This is Superfine interaction, which can be interpreted as the spin of the electron interacting with the magnetic field generated by the nucleus. So in the other case was the interaction, the magnetic, the interaction of the spin of the electron interacting with the magnetic field generated by the movement of the electron. And here is this other extra term, that is the relation with the magnetic spin, with the magnetic field generated by the nucleus. So we'll not have time to develop this so much because I still, let's see what time is it? Yeah, I think because I still want to at least give some steps how to solve the Schrödinger equation for the like hydrogen type atoms. So, but I'll give in the end, I'll give some references and you guys can, but basically the coin, but you can find this in most of the books about quantum mechanics. But coin has all this, the treatment of all these terms. So this again, this term here, with the first term, I don't remember now how I'll call, but the kinetic term, I think was H. This is about, again, alpha square is 137 square, 10 to the minus 4. So there is another terms that the distinction didn't mention. Another, let's put here. All these terms is in the distinction. There is another type of interactions, type of corrections. One of them is the spin-spin interaction when you have more than like two electrons. So the interaction of the spin of the two different electrons. So in general, this is also very small correction and give by this. So in fact, it's the interaction of the electron, the spin of the electron with the spin of the proton. So the magnetic moment for the electron and the magnetic moment of the proton. And we have this. E scalar R U P scalar R unity vector, right? R divided for R to the 2. And another type that is not present is the called lamp shift. It will give correction. This type This type of interaction was first noticed by Pauli, and this was first noticed by Dirac. But this interaction is the correction, lamp shift, the correction that comes from vacuum fluctuations. From unquantized electromagnetic field. Okay, but in general, very small too. In general, this shift that's called lamp is given approximately by this. So mc square z to the 4 alpha to the 5 over n the cube. And this is a number, a quantum number. But again, this is very small compared with the A, let's say, kinetic. So, okay, so if you want to see details about this type, see the coin energy references. Coin, I thought I had put the page here, but not coin. So the coin that we are using to show, but there is another. Oh, let me here. That especially this relativistic type of effects. This one, Gazirovich. We'll check this one. Gazirovich. Quantum physics, the name. Quantum physics. Okay. So, when comment this, after that, the Newton like give some idea about the Schrödinger equation, how you solve. We will not have time to solve here, but at least I'll give some steps, and you guys can see the solution. Oh, I think I have the pages here in the coin. Okay, but I'll give the main steps. So, change like the topic. Let's discuss the main steps from the solution of the Schrödinger equation to have solutions, only numerical solutions, okay? Because we know that the Schrödinger equation is linear, but it's linear inside That's not because it's linear that is always simple to get the solution. That's just to give an idea here. So if I have like the Hamiltonian for the atom applied for psi, and psi, yeah, the best way to get to have the solution is consider like spherical coordinates, so r theta phi. So this would give us more complete relation. Is this not use alpha? I think. Yeah, we can use alpha square nabla square from in spherical coordinates r delta phi applied to psi r delta phi plus the potential that could be the Coulombian potential V of r psi r theta phi, the energy of the system psi r theta phi. Is this alpha just defined here as being like h bar square and 2 mu, where mu is what I call the reduced mass. It's the mass of the proton plus the mass of the electron divided by the mass of the proton times the mass of the electron. Okay? It's called reduced mass. In general, this is because the mass of the proton is much bigger than the mass of electron. So in general, this is the mass of electron. It's the approximation, but let's do this.
Is that related to the fine structure constant?
In some sense, yeah. Yeah. Not this here. The fine structure constant is related.
This alpha.
No. This is not a good name. Okay. The fine structure constant is related h bar, c. Okay. Speed of light is not this. So let me change the for beta.
Oh, thank you.
Okay. So this is like step one. This is my Schrödinger equation in spherical coordinates. Step two. So how I will write the Laplacian operator in terms of r theta, and phi. So this is the general you can write in this way. 1 of r ddr r squared ddr and partial, right? Not true. Like a true. Partial derivative plus 1 sine of theta partial of theta sine of theta partial of theta plus 1 sine square of theta partial square defined. Okay, so I will use this Laplacian here in the psi system. So the third step, I'll make the separation of variables to solve this equation. So I can write the psi of r theta phi as, let's say, r of r and a y of theta phi. Okay, so what we do now is substitute the step 2 and step 3. Step 1. So the fourth step. Use 3 and two in one to obtain one radial and one angular equation. So let's call this step 4. A is the radial equation, is one of the R ddr r squared dr of r dr plus 1 over alpha e minus v. So if I have no mistake, this is the expression. So this is equal to a lambda that's a constant, separation constant. And the radial and the angular equation is this 1 sine of theta d theta partial yet because I didn't separate the two angular terms, y of theta phi plus 1 over y sin square of theta partial y theta phi. This is the lambda because I have separation, right? We could like to have this equation here, A, and this equation. They are equal. But to make the separation, I call a constant lambda. But in general, is more common, more useful. You define this lambda as L plus 1. This is just to convenience. Okay. So you can get the solution on the radial part. See this part is point page 662. Okay, I think we have the solution how to solve this equation. Just give the solution. Okay, so the solution from the radial equation is R and L. I will explain who is this N. It's just a constant minus Z R. We don't have this E. Z. I'm considering Z is equal to 1, so hydrogen atom. And beta R beta L and some polynomials that I'm calling here G and L of over beta. You guys after that take a look because I took from different. I think I took this from different sources. Maybe get some confusion, but in general is this. So this guy here that I'm calling G and L are polynomials from R beta. In this n, when you take in this solution, the n is related with the L. That's the relation with lambda, okay? It's relating this way. L plus 1, L plus 2, L plus 3, and so on. So this is the fourth step. The fifth step is to consider the angular part and separate the equation on the theta. So big theta of theta and phi of phi. Using in 4b, step 4, part B, that's the angular equation. We'll have one equation for phi over phi, d square of phi, p, the phi square is equal, these signs also for convention, m square. And the solution of this is simple. It's just phi of m of phi, a exponential I m phi. M is just a constant, okay? It's not related with the mass. It's just K, I think is better. But okay, because in the book is use M, but this M that's in the book is not the mass. So in the book, then I say in the Nielsen-Schwenk book, so I choose the same solution. That's the part that's important for us, the angular part. And okay, I have one in the angular equation, I have one equation for phi and one equation for big theta. So for big theta, the equation is this one, big theta sine of theta, d theta sine of theta, d of big theta of small theta, d theta. Okay, and this is equal to the what I'm called L plus 1. No, sorry, this is plus lambda sine square of theta is equal to minus n square. In other words, when we have the separation from the angular part, we'll have this equation from the angular equation and this equation for the theta. That's the theta is the angle in the equator, okay? This angle here. The sphere, sorry for that. Theta is this angle here. And phi is the so this is the solution for phi, and this is the equation for theta. And again, the solution here is given like a big theta of Lm of theta is sine of theta n the modulus and polynomials of Lm of cosine. Okay. Where when you get the solution, m is just 0, 1, 2, 3, and so on. And L is related with m. Like, remember this lambda here is what I'm calling L plus 1. Okay? So this is related to this. M plus 1, M plus 2, and so on. And the product of these two for the angular part. So y is the solution for the angular part of theta L of theta phi is the solution of big theta L M P of M. And when you get these two put together and make some simplifications, you find that this will give us -1 to the M to L plus 1 over 4 pi L minus M factorial L plus M factorial PLM of cosine of theta exponential I m phi. Okay. Let me just fix this. All right, this is smaller. PLM of cosine exponential I m phi. Where this P, this is the equation 763 in the Nielsen-Schwann, and this P L M is defined like x. This is where x is any value, would be the cosine of theta. So it's given by this m squared to L factorial derivative relating m and L constants dx and L of x squared minus 1 to the L. So this is equation 764. And again, you guys can look for the solutions of this in many of the textbooks from quantum mechanics. I suggest the coin, but if you guys have another that you prefer, you can see this solution for the hydrogen atoms. You find basically in all books of quantum mechanics, and you see some properties of these functions here. So this type of function here is what is called. This is like legendary. This is called legendary functions, and this other YLM in terms of this guys here are called spherical harmonics. Okay. Okay, and as you can see, like in the coin again, we'll make just some comments. Very nice properties on these functions, special functions. See coin, page 664 to 665, and page 678 to 689. So important properties here is the conservation of parity in rotations. That in general is when we change like r for r theta by a p minus theta and phi by a p plus phi. So you have like the conservations of the, you guys can see the expressions in the coin. I forgot to put, but if the these functions will be like conserved. And another important is the orthonormalization in closed relations. That you can prove that this relations, these functions are orthonormal, sine of theta, the theta, y conjugate L prime M prime of theta phi, y L M of theta phi is this L prime L M prime M. Okay. And the closed relations as well. That's written this way. The sum of infinite L and M minus L to L is given in this way. M theta prime P prime now. The closed relation is the sine of theta. It's important that we will use maybe in the future the relations. Okay. So yeah, so it's a summary, a brief review about this, how we can get like the solutions for the Schrödinger equations for hydrogen type atoms. Like we see, even like Schrödinger equation is linear, but doesn't mean that it's always simple to get the solutions. Because it's linear in psi, but it's not linear in R. So yeah, so in general, it will take you some work to have this like a complete solution, if for simple atoms like hydrogen type atoms. But my idea is to give like a review, and in the next this review, but the homework for you guys is like to see these parts in the steps that we just comment. But I think the coin is a good source to have a review. But if need in the future, if you guys want, we can like discuss a little bit more and maybe make this expression the explicit solution from this type of Schrödinger equation. Okay, so I will stop here today. I'll stop recording, and in the next lecture we'll see like the relations. Okay, these the things that we learn about the atoms, the hydrogen blood atoms, and we start make the relation with the things that we learn about photons in a cavity, for instance. So to do computation in the future, the idea is to put the atoms in this cavity and make them interact with the photons. Okay, so I'll stop recording now. So see you guys from YouTube in the next Friday. Okay. Okay, so see you guys.